Let me ask you a question that sounds super simple, but honestly, it trips up almost everyone. What's the average voltage coming out of your wall socket? You might think you know the answer, but it's probably not what you're thinking, and figuring it out actually reveals something really cool about how electricity works.
So let's really dig into this for a second. An AC signal, right, is constantly swinging. It goes from positive down through 0 to negative and back again. So when we say we want the average of that whole thing, what are we even averaging? What does that really mean?
Now, your first instinct, and it's a totally logical one, is to just average out the entire wave. But here's the thing, that's a trap. If we do that, yeah, we get a number that's mathematically correct, but in the real world, for any practical purpose, it's completely useless.
Visit youtube.com/avidsystem and don't forget to subscribe.
And the reason it's a trap lies right here, in the beautiful, perfect symmetry of the AC sine wave. You can really think of it as a tale of two perfectly balanced halves. See, for every single cycle, the voltage surges up to a positive peak, it dives back through 0, and then it plunges down to an equal but negative peak before starting all over again. It's this perfect, rhythmic up and down dance.
The positive half is a perfect mirror image of the negative half. The best way to think about it is like taking one giant step forward and then immediately taking the exact same size step backward. You end up right back where you started, don't you?
And because that step forward and that step backward are perfectly equal and opposite, when you average them out over one full cycle, well, they completely cancel each other out. The mathematical average of a pure AC signal is always 0.
But hold on a minute. 0? That can't be right. We know for a fact that the outlet in our wall is doing real work. It's lighting up our rooms, it's charging our phones. So how in the world can its average voltage be 0? This is exactly where that pure math answer just doesn't help us in the real world.
So clearly, we need a different way to look at this. And this is where engineers came up with a really clever workaround, a practical definition that gives us a consistent number that's actually, useful.
So here's the puzzle, right? How do we capture the strength of this wave in a single number if it just keeps canceling itself out? Well, what if we just stopped it from canceling itself out?
And the fix is honestly so simple and elegant. We just ignore the negative half. We pretend it isn't there. By focusing only on the positive part of the wave, we get a meaningful non-zero average. It gives us a value that's directly related to how high the wave's peak is.
And that is what becomes the standard definition. So from now on, whenever you hear an engineer or a technician talk about the average voltage of an AC signal, you'll know they're not talking about the whole wave. They mean the average of just one half of it.
Okay, so we know what we're measuring now, but how do we actually calculate it? Well, it turns out to be incredibly simple, and it all comes down to one little magic number. Now, for all you math nerds out there, this number actually comes from calculus. It's the result of finding the area under that half curve, which works out to be 2 divided by pi. But you absolutely do not need to remember that. All you need is the final number.
And that number is 0.637. This is the key. This little constant is the magic bridge that directly links the highest point of the wave, its peak, to its practical, useful average value.
So this gives us a super simple rule to live by. The average voltage is always the peak voltage multiplied by 0.637. That's it. That's the core calculation you need to know.
So the whole process is literally just 2 steps. First, you find the highest voltage the wave gets to. We call that the peak voltage. Then you just multiply that peak number by 0.637, and boom, you're done. Let's run the numbers on a couple of examples so you can see it in action. Let's say you've got a small signal that peaks at 10 volts. Easy. You just multiply 10 by 0.637, and you get an average of 6.37 volts. Now, what about a US wall outlet? It actually peaks at around 170 volts. So 170 times 0.637 gives us an average voltage of about 108.3 volts. Simple as that.
Okay, but let's just pause for a second. We have this number, that 108.3 volts. What does that actually mean? What is it equivalent to in the real world? Why do we even care?
We've got the number, but what's the physical story behind it? If we say an AC signal has an average of 6.37 volts, what can we compare that to? What does it do? And here it is. This is the key takeaway. Average voltage is the DC equivalent for moving charge. So what that means is an AC signal with an average of 6.37 volts will push the exact same amount of electrons, the same amount of charge, through a circuit as a steady 6.37-volt DC battery would. It's all about charge transfer. But, and this is a really, really critical distinction, just moving electrons isn't the same thing as delivering power, doing actual work like lighting a bulb or spinning a motor or creating heat. That's a whole different ballgame.
And that leaves us with one final fascinating question. If average voltage is the DC equivalent for moving charge, then what's the DC equivalent for doing work, for delivering power? Well, that number is arguably even more important in the real world, and it's exactly what we're going to tackle next time.
Thanks for watching.